Hello, welcome back. I'm happy we can start our lecture number 2 and come back to the course material. We will be covering today the complex infinite series and complex power series. This topic should be already familiar to you. You have seen real power series, real infinite series, and in certain way we will be referring to the reality of this series in order to bring them into the context of complex numbers. So let me write the title. So infinite complex series. Okay, let me underline it. Okay, let me put my glove in order to make it more smooth. So I'm putting my glove on. I have just to use my tablet, drawing tablets more effectively. And now we can start writing. So, what is an infinite series? So, a complex infinite series which can be represented as, let's write it down, so this will be like this. N is equal, 1 to infinity, and here we have the numbers an. So the number an, of course, is a complex number, and we can also write it down. An has the real part, and it also has the imaginary part. So such an infinite series can be seen as the expression, the two real series. Namely, we can rewrite this series. N is equal 1 to infinity, an, using the real and imaginary part of the coefficient an. We can rewrite it down as infinite series of the real part plus I, and this will be infinite series of the imaginary part. So we can now say what is the convergence. So the series, called this series star, the series star, and the series converges if and only if, use this symbol, if the real part of star and the imaginary part of star, so let me move it down. Imaginary meaning, so what does it mean? That means simply this series n is equal 1 to infinity alpha n, and then this series n is equal 1 to infinity, and this will be beta, and both converge. Of course, we have also the notion of the absolute convergence of such a series. We also say that this series, the complex series n is equal 1 to infinity, an converges absolutely if the real series and in this case this is the series n is equal 1 to infinity, absolute means modulus of an, that's a real series, converges. So this is, we say that it converges. Good. So we have several statements that we should say. Maybe let's notice the following. So the following concepts that we have: the tests for convergence. And that's a little funny because I will start with the test for divergence, which basically says the following. So put it like this: necessary condition for convergence. So in this case we have here like this: if series n is equal to 0 to infinity, and I put here an converges, then we have here the limit. Sorry, it's kind of slow. Okay. Then limit as n goes to infinity and of an must be equal to 0. So that's the necessary condition for convergence. We call it necessary convergence condition, or simply divergence test, because you can use this condition here, this condition that is, if such a limit is not equal to 0, then of course the series must be divergent. That means not convergent, divergent. So that's the first observation. So necessary conditions for convergence. Then we have several other tests, such as the comparison test. Let me write, for example, this one. So A, put it like this: if you have two series, let me use alpha. Okay, given two real series, and then let's write it down. N is equal 1 to infinity, and this will be alpha n, and then you have here another series, n is equal 1 to infinity beta n, such that both of them are of non-negative alpha n, and beta n dominates, means is larger than alpha n. Then we have if the series beta n converges and the series alpha n converges. And also, that's my first statement, and the second statement is that if the series n equals 1 to infinity alpha n diverges, then the series beta n diverges. So we can write a little simple results, call it like this proposition. Let n is equal 1 to infinity sigma a n be a complex series which is absolutely convergent then this series also converges. And that means simply that absolute convergence is nothing else than stronger requirement for convergence. There is convergence and there is something which is called absolute convergence. So it is with additional requirements. So I do the proof, which is elementary, based on the above comparison test. Notice that we have for every n belonging to natural numbers, and we have absolute value of alpha n comma absolute value of beta n is smaller or equal than absolute value of a n. Here, of course, we have here a n is equal alpha n plus I beta n. And that means, in particular, of course, both of them are larger than 0, larger or equal than 0. So by using the comparison test, which is here described, and this is the number 1, you can immediately write the following that then since this series n is equal 1 to infinity a n converges, then by comparison test both the n is equal 1 to infinity absolute value alpha n and absolute value of beta n converge, and that means so they converge. So the series alpha n and beta n converge, because we know it from the real series theory that in such a case the series alpha n and beta n converge, and that implies by the observation, by the definition of the convergence, that's our definition, that these two series converge, so the series, original series, also converge. You see, this one is, let me write it down. So you see, this is the converge. That means the original series converge. So we got it. So we have the first statement related to it. So now, of course, once we have it, so we also have a couple of other easy to deduct in the similar way as we just did it, using the real and imaginary part. Easy statement. So maybe let's write it down, the ratio test. They also call this test the D'Alembert test. And in such a case, we just simply write it down. Suppose an is not equal to 0. Then, if the limit n goes to infinity, and here we write it down, absolute value means modulus n plus 1 divided by an, this limit exists, and is equal to the number L, which is smaller than 1, then the series, and let's write it down, n is equal 1 to infinity, and we write it down, an with absolute value converges, maybe let's use the notation, let's say exactly our symbols, and put it like an without absolute, and we just simply write converges absolutely. Oh, like this. So this series converges absolutely. Okay, so of course you can say, okay, in this case there is a kind of a inconvenience because an has to be different than 0, but you know, there's always another test that doesn't require it. So this will be called the root test. Put it like this, test. Test. The root test. And in the root test, just simply, if limit as n goes to infinity, and I put it like this, nth root of an exists, I put it like this, exists is equal to L, which is smaller than 1, then the series sigma n is equal 1 to infinity an converges absolutely. Converges absolutely. So that's a one little thing that we should understand, that in this case, this test of course talks about the convergence, but there's also a version which is related to divergent. If this L is larger than 1, then we have divergence. So let's put it again. If L larger than 1, diverges. So let me show you again. This means there is a divergence involved. And of course, if L is equal to 1, we call it inconclusive. If L is equal to 1, inconclusive. And sometimes they just tell you, just say the test failed. Test failed. Coronavirus test failed. Yeah. Very good. I'm still waiting for my results of my coronavirus. They did it on Wednesday, and I'm still not getting anything. Who knows? Maybe I'm infected. In any case, let's move further. So this is exactly kind of the statements that we'll be using later when talking about the power series, and we will be talking about the radius of convergence in a moment, so I hope that we will remember them. So this test, by the way, also has a name attached. It is called the Cauchy test. Cauchy test for the convergence. So now let's go and let's make a couple of statements. So first of all, product not nice. Product of two power series. And underline. So we take one power series, complex, remember everything from now on is complex. Start it with 0, it's more convenient. an an and take another power series n is equal to 0 to infinity bn. Then we can define the product series, the product of these two series as a power series and write it down like this. N is equal 1 to infinity. This will be Cn, which will be equal exactly. I take here the n is equal 1 to infinity. An times, and I put here n 0, 0. N is equal to 0 to infinity. Bn by the formula that Cn is equal to the k is equal to 0 to n, and this will be ak, and this is bn minus k. bn minus k. The change of the indexation from 0, it is just for the convenience. I do not want anyone to be confused. We will be mainly talking about the power series, and when we are talking about the power series, of course, since we have the powers starting with the 0 power, it was always more convenient to start the indexation of your terms in your infinite series from 0. So this is the power series. So one of the things is the following. So of course remember that this is actually the power. Let's say this is actually, if you have the limit, so you have to understand. Maybe write it down like that. So we have the associated value. If you have a infinite series, complex infinite series, which is convergent, then of course, what does it mean? This series. What is representing this series? This series will represent a complex number, which is exactly the sum. Let's say the limit of the partial sums. The limit of the partial sums. This is exactly the same definition that was considered in the calculus earlier when you were talking about when you were learning about the real infinite series. So you should understand that every infinite series represents a number. So if you write the symbol like that, and you have here one series, another series. So let me show you which one. If you take the product of these two series, and if you write one series, another series, you multiply. That means the first series here represents a number, this series represents the number, and of course that series also is representing a number. In our case, all those numbers are complex numbers, so in this case actually it denotes an equality. I can clearly state this particular property, and maybe we will do it in the form of the proposition. Let's say suppose an, n is equal, start off, let's continue with 0. An and n is equal 0 to infinity bn, we two infinite series, so two complex series, such that, okay, maybe like this, so 10 we have. Maybe start with the A. N is equal 0 to infinity, and I put here an plus bn is equal to an, n is equal 0 to infinity plus infinite series n is equal 0 to infinity, and this will be bn. Then we have equality where the convergence of any two infinite series in this formula, in the above formula, implies the convergence of the third one and we have the equality of numbers of their values, like it is described here. So that means that if you take the sum of the coefficients and to make it into an infinite series, then if this series is convergent, for example, if Bn is convergent, then the An will be also convergent, or any two of these three series. So this is my number 1. Show you again. This is my number 1 series. This is number 2. This is my number 3 series. So any of them. Similarly, of course, since the same, we should write it again regarding the, put it like this, B. I put it here, An, so this is 0, infinity, and now I have here Cn, and rewrite it down, the same thing, 0, infinity, An, but that time takes the product. So Cn is exactly the formula that was given here, so this is Cn, look here, this is my Cn, that's my Cn, by this formula, call it like this, double star, yes. Cn given by double star. Cn is given by double star. Then we have exactly the same, so the same conclusion as in A takes place. The same conclusion. So this is called the product of infinite series. If one of, let's say, if two of these series converge, then the third one converges, and vice versa. if you have, for example, the no vice versa. Yeah, that's it. So this is, and maybe put here additionally property that you can always take a constant out. So if I put here a number, any complex number, call this complex number D, and I put here An, n is equal to 0 to infinity, then you can take this complex number D out, and of this expression, and you are getting here another. So this will be like you can take D out from the summation. So this is kind of the distributivity property. So you just take this out. So this will be your out out and stands there. So of course, if one of these series convergent, then the other one will be also convergent, of course, only in the case when d is not equal to 0. So the same similar conclusion is true. So these are the basically properties of this infinite series, and maybe we should now introduce the notion of the power series, complex power series. But in order to do it, let's take a short break and put it in the next video. Thank you.